And I'd like to start by thanking Pete, all the organisers and the CCDC for giving me the opportunity to come and talk to you today. It's an enormous honour to be part of the 50th year celebration of the CCDC. I arrived in Cambridge in 1976, and as Aurora said, it was already here. It's always been here. It's always been an enormous part of the support network that I've had. So what I want to do today is perhaps broaden the discussion a little bit and think about where we've come in the last 50 years in terms of structural chemistry, not just the CCDC, but the broader remit, and try and look a little bit forward in where we might go for the next 50. Aurora's booked for the 100 years. I'm sorry, guys, I'm not going to make it. So let me start at the beginning, and as actually most things happen, I'm going to start with a quote from Jack, because all the research I've ever done, I've discovered that Jack's thought about it and talked about it at least 20 years before I tried to do it. So thank you very much, Jack. So Jack was amongst the first to say that crystals are not static, rigid molecules. There's movement in the lattice everywhere above absolute zero. So we have atomic vibrations, we have dynamic disorder, we have complete chemical reactions going on in the solid state crystal. And particularly from the CCDC and the crystallographic point of view, we have single crystal to single crystal transformations going on. So crystals really are dynamic. They're really exciting. They're not the graveyard, as some people say. They actually point the way for future science. And if we're thinking about single crystal to single crystal transformations, there are a number of ways of doing that. We are restricted to the solid state, of course. Therefore, chemical reactions in the solution sense aren't so readily available. But we can use other external media to induce those changes. So we can change temperature, we can change pressure, we can change magnetic and electric fields, and we can change light to induce these chemical changes. And here's an example of a light-induced change. Here's a single crystal that's yellow. We shine light of a particular wavelength on it, and it goes red. There's a chemical transformation there. So that's easy, and I'm going to spend most of the time talking about light interactions. And the reason we do this is it's probably the easiest of the ways of causing these chemical processes to occur. Light is very easily obtainable. We've got a very wide choice of sources. We can go from 100,000-pound lasers down to LEDs, and the group have used Christmas tree lights. I promise you we have. So we've got a great deal of accessibility to different wavelengths and different intensities. If we're looking, however, at the processes that we might be able to affect, and look at them crystallographically, we're probably still looking in this region where we're looking at species with lifetimes down to microseconds rather than the faster systems, which is still very much the realm of spectroscopy. We can talk about FELs and the next generation, but I think for the moment we're probably crystallographically restricted to systems with lifetimes of, let's say, hundreds of nanoseconds. But let's go back to the beginning. Photochemical reactions have been known for rather a long time, indeed from the 19th century, and were reviewed or the solution work was reviewed by this article in 1989, but the first solid state comprehensive studies were in fact carried out by Cohen and Schmidt, and thank you, Joel, you've introduced them. Those two fathers of structural chemistry did the first comprehensive studies on 2,2 cycloaddition reactions in the solid state, where you take two monomers with double bonds, shine light at them, and you get this 4-atom unit. And they came up with a number of parameters which hold very much to today. For a solid state reaction in general, you need the process to follow the minimum energy pathway. If that has to happen, you want the least amount of atomic movement that's possible, and you want, from the crystallographic point of view, to remain in the crystal environment. You don't want to destroy that. More from the crystallographic point of view, these were the parameters that Cohen and Schmidt set out, were reactions between adjacent molecules. You'd expect the structure of the product to be related to the orientation of the monomer molecules. There was a general view that the double bonds in these 2,2 cycloaddition reactions should be parallel, and a statement was made in the paper that the double bond should be less than 4.2 angstroms apart. So let's have a look at that. The CSD, latest search from a couple of weeks back, there are 67,938 hits that pretty well correspond to those parameters. We'll take the 4.2 level there. So lots of molecules that should undergo 2,2 cycloaddition reactions, and if we break those down and look at the torsion angles, there are over 2,600 hits where those double bonds are parallel, and in fact these have to be parallel by a centre of crystallographic symmetry. So lots of molecules that should undergo solid state 2,2 cycloaddition reactions. A few years ago we had a look at 5 of these molecules. It's not quite correct there. 4 of these hadn't been studied before to see if they did undergo 2,2 cycloaddition. The transenamic acid had, but we used that as the benchmark to make sure we were doing the experiment correctly. We had a look at these. If you look at the carbon-carbon intermolecular distances, you can see they all obey the criteria. They're all below 4.2 angstroms. So they all ought to go. We tried 3 days light irradiation. The transenamic acid we knew should go, it went. The coumarin also went, the other 3 didn't. And to prove that they did, we have powder patterns, and you can see for the cinnamic acid and the coumarin, the changes in the powder pattern at the end of 3 days, where the black is the original monomer form, and we have the change to the cycloaddition product. And I should say here that the work was actually carried out by Hazel Sparks, who did a PhD with me, but was co-funded by the CCDC, and we had the pleasure of Greg Shields and Frank Allen as her co-supervisors, and I'm enormously indebted to both of them, and particularly Frank for mentoring me over many years and very much driving a lot of this research forward. And if you look at the coumarin, you can actually also do that in the single crystal. With a mercury lamp, you can see that we get a formation of the 4-membered ring there with a shortening of the carbon-carbon bond and a reduction in the cell volume of about 6%, going from the monomer to the dimer product. So fine. Why didn't the other 3 go? Well, there is always this argument, it's crystal strain. The geometry change would be too big to allow the crystallinity to be retained. what does that actually mean? Well, it actually means something about intermolecular interactions in the monomer starting material being too strong, perhaps, and you need to get over too much of an energy barrier for the process to occur. The other idea relating to this is that there needs to be space in the crystal for this to happen, and the concept of the reaction cavity, that space in the crystal, was again first introduced by Cohen in 1975. So there is this recognition that the crystal encapsulates the photoactive part of the system, and any atomic rearrangement occurs in that cavity. This was further developed, the idea of the reaction chemist, by Ohashi, and I have to do a frank joke. Ohashi, famous Irish crystallographer. I laughed. Who looked at the first cobalt oxamine complex, where in fact by X-ray damage there was actually a cleavage of this cobalt carbon bond, and with that unit taken out you can see the cavity within the structure. So that's, if you like, the reaction cavity that allows that process to occur. So that's the sort of background to the work. What I want to spend the rest of the time talking about is the idea of developing that further, the idea of photocrystallography, and particularly applied to linkage isomers in the solid state. And really the objective of the research is to bring the dimension of time into the crystallographic experiment. One of the arguments put about by non-crystallographers is that crystals are dead, they're static, they tell you about the starting material, they might tell you about the product, but they don't tell you about how you get from A to B. What we'd like to do is actually follow that process, and in a sense we've already done that, and many others have already done that on the 2,2 cycloadditions, but it's an irreversible process. What about looking at reversible systems? And we can do that in two ways. We can use steady state methods of photoexcitation and generate metastable states, or we can use faster probe techniques to look at transient species with very short lifetimes in the, as I was saying earlier, multiple numbers of nanoseconds. I'm going to concentrate today on the easier experiment, the slower experiment, generating metastable states. And what I mean by this is, if we look at the energy curve, the reaction coordinate, we're interested in the structure of the species here. That is, it can be trapped in that metastable region, and then we can look at it crystallographically. And Phil Coppens, who pioneered this area, basically defined photocrystallography as the technique by which a three-dimensional metastable or excited state structure of molecules within the crystalline solid can be determined crystallographically while being activated by light. So let's look a little bit more about the steady state experiment. There are many inorganic systems that form metastable intermediates, generally stabilized by low temperature if you irradiate with the right wavelength of light. And my definition of metastable is something that lasts longer than the duration of the X-ray experiment, which now can be a matter of minutes and soon will be a matter of seconds. However, we use the cheap method. We are going for the 50 pence LED, not the £100,000 laser. How do we do these experiments? Well, you can do them in your home lab. You basically put your LEDs in a ring on the crystal cooling apparatus round the crystal, leaving in this ring space for the X-rays to come in and space on the other side to detect the diffraction pattern. And then what you need to do is a ground state data collection before any excitation, but at the temperature that you wish to carry out all the experiments. That gives you a benchmark ground state structure. You then irradiate the crystal for a period of your choice to attempt to generate the metastable state, and then you recollect the data, you hope with some of the metastable state present, look at the electron density map, see if you can see a proportion or total conversion within the crystal, and then play with the temperature until that occurs. And we thought linkage isomers would be a good place to start because you actually get real atom movement here. So a whole set of ambidentate ligands, those are ligands that can be bonded to the metal in more than one way. And you can see an example here. There's a nitro group bonded through nitrogen. In solution, it's been known since the time of Werner that if you irradiate with light, you can convert to the O-bound nitrito form. Can you do this in the single crystal? Well, the answer is yes, you can, and Phil Coppens did the first experiments on the iron nitrosyl system where irradiation with one wavelength of light gave you this side-bound NO, and then different wavelength, you actually get the inversion to an O-bound nitrosyl. And since then, there have been examples of SO2 doing this, of the nitro doing this, as I showed on the previous slide, and even DMSO doing that. And when we started looking at these, there were a number of examples of where you were getting conversion, but you weren't ever getting complete conversion. And you can argue that if you want this to be useful, if you want to apply it, you might want to switch. You want it to go 0 to 100%. Something in between isn't really what you want. How do we go about getting to 100%? And you're doing this in the single crystal. All these examples that went showed a change in cell volume, normally an increase of less than 2%. Is this telling you something about the packing? Is this telling you something about crystal strain? How might we do this? Well, we can use the idea of the reaction cavity to give you space for this to happen. And we can do it in a number of ways. You can use bulky ligands that define the crystal packing, generate the cavity. You can use salts, which have bulky inert ligands, groups that actually define the packing that give you space, or indeed you can encapsulate your photoactive species in some sort of framework. And Neil Champness and Mike George have done some elegant work with metal organic frameworks allowing this to happen. So what we want to do is design crystals where there's this cavity, where there's a minimum amount of non-covalent interactions to allow this to go without having to go over a particularly high energy barrier. And we decided to look at the nitro to nitrito species, and here's an example of a partial conversion with 400 nanometer light. You can see the N-bound partially goes to O-bound. How do we get that up to 100%? And it's worth looking at the CSD for this. So here's the interaction for the NO2 group for all types of hydrogen bond interaction. And you can see that there's a range of distances. So it looks as if the energy map for this surface is actually fairly shallow. So maybe not too directional in terms of the interactions. But let's go back to looking at what sort of ligands might do it. So here we've got a nickel nitrosyl complex with a bulky phosphine. Well, the idea of introducing the bulky phosphine is to introduce the idea of this dominating the packing. We always combine our experiments with spectroscopy, and we looked at the Raman of this system, and you can see that there's actually a change around 800 nanometer, or centimeters to the -1, sorry, with white light, which suggests there might be a change. And in fact, if you do this over time, you can actually see the interconversion of one band rising and one falling. And in fact, you can also look at the temperature range and again see those bands changing. So it looks as if something happens in the solid. Does it happen in a single crystal? And the answer is yes. In this system with 400 nanometer light between 60 and 180 K, this goes through to 100% conversion. So it's the first system that actually does 100%. So technically we now have some sort of counting mechanism where that might count as a binary 0 and that might count as a 1 in some sort of molecular computing, usually left for EPSRC applications rather than audiences of this caliber. There's nobody from the EPSRC here, is there? So also, how fast does it go? Within the single crystal, you start with your N-bound. In about 10 minutes, you get 50% conversion. So here you have your disordered model. And in 20 minutes, you go through, in the single crystal, to the O-bound form. And if you look at the displacement ellipsoids, they get a little bit bigger, which might suggest some sort of crystal disruption, but you can just warm this and go back and recycle it. We've done it 20 times, I think, without any significant crystal deterioration. So we do have a fully reversible process. And if we look at the structure, you can actually see there are some hydrogen bonds. The NO2 oxygens are acting as hydrogen bond acceptors, but not terribly strong. And if you look at the fingerprint map, which illustrates whether or not there are hydrogen bonds, you can see that these little sharp peaks suggest that there are, but they're not particularly strong. And as Jack says, atoms have got to be somewhere, so not a particularly strong interaction. But if you take the NO2 out and recompute the structure with the cavity space, you can see that we have these reaction cavities that are big enough for the NO2 to rearrange. So that works fine. And spurred on by this success, you can do this from a number of similar complexes, with slightly different conditions, but we now actually have a series of these two molecules both go to 100%. This one goes to 80% conversion. So we've achieved one aim of getting systems that can switch reversibly 100%. So can we do more than this? Well, we went on to a related system. If I flick through and show you the picture, this molecule we took crystallizes at room temperature with both forms present, 78% of the N-bound and 22% of the O-bound form. So at room temperature you have this mixed species, but can you play the same game we've done with light with temperature? And the answer is yes, you can. If you cool the crystal down, below 166 K, you get 100% of the N-bound form, so a clean N form. And you can then also warm it back up, and you go back to the 78-22%, again without particular loss of crystallinity. And you can even take it higher, go to 42% at 370 K, above which it decays. So we have that equilibrium. We can do the photocrystallographic experiment, and starting at 100K with 500 nanometer light, we get this 100% switch in about an hour, and you can see the electron density of the N-bound coming in and the O-bound coming in and the N-bound decreasing. And you can play with the temperature, do a series of parametric studies, and optimize the highest temperature at which this metastable state continues. What this allows you to do then is single crystal kinetics on these systems, so you can actually monitor a number of reflections to look at the kinetics. And what this tells us, I won't go through all the numbers on here, as I know Pete's standing up and looking nervous already, that effectively this number is the one we want to concentrate. It's near 1 if you use the JMAC approximation for solid state kinetics. That's basically telling you that each photon interacts with one molecule. There's no cooperativity in these materials, and therefore you get an idea of what sort of experimental conditions you want for this process to occur. What it also allows you to do is play with the variable temperature idea and start measuring kinetics at different temperatures, which allows you to determine the activation energy, and that comes out at 48.6 kilojoules per mole, which is, I think, has the right feel. It's also in remarkably good agreement with computational studies that we've done. So that's pretty well where we are in trying to design these systems, but I would like to emphasize that the CSD is fundamental in all this. We always use that to look at the likely molecules that will transform and the cavities and the energetics in these systems, and I'm sure that's going to be a very important use of the CSD in the future. So just to summarize, we've developed the technique that allows us to look at these metastable systems. We've got the first 100% conversions on these materials, and I think what we've established is that both steric factors are probably most important, but there are also kinetic factors that we have to consider when looking at these transformations. So I'd like to finish by thanking the team. We actually have a program running on this at the moment. What I've talked about today, Hazel was a PhD student, as I said, with me and with the CCDC a few years ago. Most of the work I've talked about was carried out by Lauren and Mark. Mark's now at Diamond, Lauren's now postdocing in Bath, but I'd like to thank the whole team. But I would also like to give my sincere thanks to the CCDC for all their support over the years, and also you for your kind attention. Thank you.